So because this is a binary search tree, it of course makes sense that we want to be able to search through things in the tree. So the idea of this is actually going to follow pretty similar to the insertion. You'll see that there's a lot of parallels between these two methods. The idea is that we're going to create a search method, and it's going to, of course, refer to an auxiliary function. That auxiliary function is going to take in the root value the root node as well as the value that we're searching for. And then the search auxiliary function is where all of the exciting parts are going to happen, so the actual searching for the value. And basically the process of searching the value is the process that is finding where we want to insert a value, right? It's basically the same sort of process with some small modifications to it. First modification is that if the current node that we're at is none, well, then we didn't succeed in finding our value and we return false. If you think about it, if you're looking at a tree and you're trying to search for a value and you keep, moving through the tree and eventually you end up at none, it means that you've reached the end of the tree. There's nothing left inside of it, which means that you have not found the value that you're looking for, right? Otherwise, there's basically three cases, right? We've either found the value that we're looking for, which would be if the current value is equal to the value that we're searching for, in which case we return true. The second case is that the current thing that we're at is less than the value that we're looking for. And if that happens, we're going to do a recursive call. And the recursive call that we're going to do is to the right-hand side, right? It's to the right-hand side because the current value is less than the value that we're looking for. If it's less than the value that we're looking for, then it must be on the right-hand side, since the right-hand side is bigger values, right? Similarly, if this wasn't the case, it would mean that we want to go to the left-hand side. We want to find values that are smaller, right? So in this case, we would do current.left with the actual value itself. That's really all there is to it, right? Very similar kind of iteration to the insert auxiliary. And you'll see that this is basically the case if we ever want to iterate the tree to look for something or to find something. This is basically the way that we're going to do it. It's very standard sort of iteration every single time. So it's the same sort of deal as our insertion. So with that in mind, let's give this a try and see what happens. I'm going to do a search. I'm going to search for the value 40 in this case. I know that 40 is in my tree, so we should get a value of true as a result. Let's go ahead and take a look. So I want node.py. We see that that's true, right? Now if I change this to say 400, we should get a false as a result. And that's exactly what we get, right? So you can see that it does seem to reasonably search through our search tree, right? This is going to have a very similar time complexity to our insert, right? It is O log of n. With that caveat that I mentioned before, the tree has to be balanced. Again, we'll talk about how to balance a tree a bit later on, but generally this is going to be an O log n based time complexity for our search. It says we have a bit of time in this video. I'll also talk about deletions, and you'll see that deletions are very similar, but there's an interesting sort of case in the deletion that makes them a little bit more complicated, but we'll talk about this in some detail, right? So the idea of a delete is that we want to delete a specific value from our tree. So we're going to follow the same sort of pattern as our insert. We're going to update the root to be the result of deleting an auxiliary, right? Starting at the root and the value that we actually want to delete. And then I'm going to define my delete auxiliary. It's going to take in the current node that we're iterating from, right? And the value that we're looking to remove. Our first step here is to try to find the value that we're trying to delete. So if the thing that we're looking at is not current, right, we're just going to return current, right? So basically, if the value is going to be none, this is basically a similar way of saying that, right? The other cases that we want to take a look at is current.value being greater than the value that we're searching for. In this case, we're going to do similar updates to the insert, right? We move to the left, doing our delete auxiliary using current dot left and the value that we're searching for. And then same sort of deal with the insert. On the other side here, we're basically going to say else if current.value is less than the value that we're searching for, we do current.right equals self.delete auxiliary, right? We do current.right and the value itself. And then finally the else. So on the else, we found the value that we're looking for. So all of this was basically trying to find the value that we want to delete. This else here is we found the value that we want to delete. Now, we have to think very carefully about what we do when we delete the actual value itself. Consider a case where a node has no children. In this case, when we delete the node, we don't need to replace it with anything except for none, right? Because there's nothing below it. So we don't have to worry about, things being below it on that actual deletion itself. In the case where the node has one child, say a child on the left or a child on the right, what we need to do is we need to take that child and basically replace what we're deleting with the child itself. That would effectively remove what we're deleting and replace it with the thing that's below it, right? So those two cases are pretty easy. I'll just show you those right here. So if not current.right, then we're going to return current.left. So basically, if it doesn't have a right child, then we're just going to return what would be on the left-hand side. So it's left child. So basically, we're replacing what we're deleting with the thing to the left of it. And then similarly, if it doesn't have a left child, we're going to replace it with the value to the right of it. So basically, if there's no left child, we just take what's on the right and we replace what we're deleting with the thing that's on the right. Now, here's a bit of a problem. What if it has both a left and right child? What do we do? The case of what we do for this is we're going to replace it with the next, what we would call in-order successor. And basically all that means is that we want to find the value that is closest to the value that we're deleting, and that's the one that's going to replace the value that we're deleting. The reason why we want to replace it with the thing that's closest to it in value is because that value is going to sort of guarantee the properties of the binary search tree, right? If it's as close as possible to our current value that we're deleting, then everything should remain in that same property of less than on the left-hand side and greater than on the right-hand side. Additionally, it should help improve the possibility that our tree remains balanced. Because the value is pretty close to the one that we're deleting, it's going to ensure that the properties sort of remain and the structure sort of remains as close as possible to what it was before the deletion. That's the main idea of why we're trying to do that. Now, how do we find that value? Well, the idea is that I'm going to take a look at the thing that is to the right of my current node. And what I'm going to do is I'm going to iterate the left-hand side of that to find the value that's closest. Remember that the right-hand side would be greater than the value that we're deleting. And if I go to the left-hand side of that, it's going to show me things that are smaller than something bigger than the value that we're deleting, but it would be like the smallest thing that's bigger than it, if that makes sense, right? Like it's the smallest value that's larger than the one that we're deleting. We call that the in-order successor. So the way that we get there is we say while temp is not none, right? And temp.left is not none. We just do temp equals temp.left. So we move to the left-hand side, right? And then what we're going to do is basically we're going to say the current dot value is equal to temp dot value. And then we're going to say current dot right equals self dot delete auxiliary current dot right temp dot value. So this is a little bit interesting, right? Basically, what we're really saying here is we're saying that once we've sort of located that value, we're going to set its value to replace the node that we're trying to delete. And then basically what we do is we remove it from its original location. And I realize that this piece should be unindented here. There we go. So we find the value, and then basically we replace that value with the one that we're trying to delete. And then we delete that value from where it originally was. So basically this second deletion here is just to ensure that we don't have a duplicate of the value that we are replacing our original deleted value with, right? So it just reduces that possibility. Once that's complete, we simply return current, right? I think I would do this just right here. There we go. Return current, just like that. And that should do it for us, right? So let's go ahead and give this a try. I'm going to try to delete the value 40 as a start. That one should be an easy one. 40 is at the bottom of our tree itself. So in this sort of situation, we get back a value of none because in terms of like the actual return of the delete, there isn't any sort of return. But basically what I could do is I could say print out b dot root dot, and we'd have to just sort of like search for where 40 would have originally been, right? So 40 would have been to the left of 50, right? And then from there, it would have been to the right of 30. If that value is none, then we have removed the value successfully, right? Now here's a fun one. What if we remove the root of the tree? If we delete the root of the tree, it's got 2 children for it, right? So we should be able to see a difference in the actual value itself here. You see that the value became 70. Do you see that the value became the next largest value in the tree, right? So that's an example of how that deletion is generally working. Because 50 had 2 children, we went through and we picked the value that was the largest out of those children and replaced it with it, right? So that's generally what's happening here with the deletion. One final piece here, time complexity for deletion generally is going to be about log of n, right? Again, with that caveat that things actually need to be balanced, but that's generally what we're going to have for our time complexity. So that gives us a delete as well as a search. And now we can discuss a little bit more about iterations, which we'll take a look at in the next video. So thanks so much for watching. I'll see you in the next video.